Hi everyone, and welcome back to another Math Research Live. Hi everyone, with me, Charlotte Aten. It sounds like I'm experiencing a little bit of audio feedback from another device. Okay, so let me just stop this. That's one of the drawbacks of not doing this for a while, I guess. I forgot that actually it was my device. Yeah, you might have thought that I was gone forever, but I did just get COVID, and that kind of slowed me down for a while. But here I am. Before I get too much into it, I want to also check in with people and see if this this air conditioner in the background is too overwhelming. Can people hear me over the air conditioner, or is it just extremely annoying? I'm just trying to figure out if I should keep it on. Hello. How's it going? So, yeah, if you have an opinion about the audio, just let me know. Sorry about the feedback a second ago. I just totally forgot that I have to turn off my own audio on my machine in order to do this. All right, well, I guess I'll just jump right into it. So, as I indicated when I was advertising this a little while ago, I wanted to talk about this paper, which I've linked in the chat here. If you can't get a copy of the PDF for whatever reason, just maybe let me know, or just ask maybe somebody else who knows where to get things. Unfortunately, I couldn't find a direct link to a PDF online. Whenever I can, I usually default to that because obviously that's the most accessible thing for everyone. But unfortunately, I didn't have something. I didn't have such a link this time. But well, you can also look here. If you even look on, when I post this on YouTube, maybe you can even maybe just pause the video if you want to see a certain part of it and you can't get access to it any other way. But yeah, so if you've been following what I've been up to lately, then you'll know that I went to Korea earlier this summer, and that's where I got COVID, and I was kind of out of the swing of things for a while. But I am now back to it, and one of the things that I wanted to think about while I was in Korea was this formula for the number of Latin squares. So there are a number of different ways of finding out how many Latin squares there are of a given size, and in case you don't know what Latin squares are, I'll remind you. As always, just ask me pretty much whatever you want, especially if it's related to math or academia or anything like that. But I wanted to think about this formula for the number of Latin squares, and so I had found this paper. Well, it's a note, I suppose, that was apparently Jia Yu Shao and Wanda Wei from 1990, in which they give a formula for the number of Latin squares of a given size, and as you can see, here's the formula right here. And so what I was thinking for today, assuming that we don't get off on some kind of, tangent, although if we do and it's, something interesting, that's totally fine. What I was thinking for today was that I would just go through basically, reminding you of what Latin squares are, and looking at why this formula makes sense, and then thinking about how we could possibly generalize this to count higher dimensional Latin cubes, and our permutations of rows and columns counted separately. Yeah, so in this one, it's not going to be up to any notion of equivalence. So actually, yeah, if you look right here, so they say what a Latin square is here, which you can also read. Although I'll remind you like on the board in a minute as well. Oh, look, it cost $5 to have this in 1992. But yeah, so it says that it's just the number of Latin squares of order n. It looks like they're not counting any kind of equivalence. So if you permute the rows or the columns of the Latin square, then that's a new Latin square as far as this number is concerned. But yeah, that's a good question. Some of these questions can be very different depending on oh yeah, this is, so it is counting quasi groups. Okay, maybe I'll actually go to the board now to answer this better. So this is counting the number of quasi groups of a given order, but not up to isomorphism. So okay, so maybe just to remind you, well, I guess first what I'll do before getting into the Latin square quasi-group thing, the first thing I'll do is I'll actually just talk about the counting issue for magmas, or for just arrays. So if I have say I have some underlying set, which I usually choose to call A, and it has n symbols, which I'll just choose to be 1, 2 through n, then I can make a multiplication table, which definitely isn't the usual multiplication of numbers, where I make an n by n multiplication table like this, and if I choose for each of these entries something to put in, and I'll just make some arbitrary choices, maybe this is 2, this is 5, maybe this is whatever n is, 0, well, I don't want to start with 0, I guess, no 0, 1, 3, whatever, you get the idea. If I fill in each of these spots with one of the symbols, then I'll have this n by n table, and such a table or such a multiplication rule is called a magma of order n. And so, well, the total number of magmas of order n oh yeah, don't get me started again on all the things about what's a magma when it's above ground, or volcanoes, or all of that. We've actually discussed the terminology on stream before, I think. But the number of magmas of order n using these symbols 1, 2 up through n. Well, if you think about it, in each of these little spots here, I have n choices. Oh yeah, the magma computer algebra system. I'm actually more partial to Sage Math myself, but I gather that magma is also a perfectly cromulent computer algebra system. Oh yeah, and cromulent is a very mathematical word, by the way, because as some of you may remember, it was quite popular with the original writers on The Simpsons, and as I'm sure you know, many of them had math PhDs and so forth. So it's a cool time. All right, so there's n choices for each spot, and oh good. Oh yeah, so yeah, we love all things magma here. Yeah, yeah, absolutely. Yeah, so we have, I'm sorry, I was just started to zone off thinking about different color maps. Yeah, I mean, yeah, I don't know of any mathematical lava, actually. The conversation we had previously was that there's something called isogeny volcanoes in, it was algebraic geometry. It had to do with elliptic curves. It was in the theory of elliptic curves. And I had discussed looking at, somebody recommended a paper to me, I think, on one of these streams earlier on, and I looked at, I wanted to do something with like isogeny volcano magmas, and I had like a specific definition in mind. But I think that it would be more fun to do that with someone who actually has a background in elliptic curves. And so I'm currently waiting for that to happen, but perhaps someday someone will want to mess around with me and write a paper that's just completely about this, this silly idea. Okay, so there are n choices for each of these spots in this array, and then, well, there are, there's n choices in this spot, there's n choices in this spot, there's n choices in all the spots, and there are n squared spots because it's n by n, and so that means that the total number of magmas of order n is, for each of these spots you have n squared choices, and you make those choices, or each of those spots you have n choices, and you do that n times, so it's n to the n squared, right? Because like if you have n choices here, then you multiply that by the n choices here, and so on and so forth, so it's n to the n squared power. It's definitely really nice when there are names inspired by things in real life. Sometimes people complain about oh, why are things in math named all sorts of technical things, or why are they named like butterfly, or like whatever the thing might happen to be, actually I don't know of an object named a butterfly, but there is a butterfly lemma. But there's all sorts of things like this. You're like, oh, why call it that? It makes it less accessible. But the alternative really is that if you try to name things by like literally what they are, everything turns into like some kind, like everything would be named like symmetry, structure, pattern, decomposition. It would just be complete gibberish. Like there's nothing that like the number pattern approximation thing, like it's just there's there's only so many words for some kind of pattern before it just sounds like a meaningless assemblage of words. So you might as well choose names that are more colorful and kind of have some kind of story in mind, or some just some random association that helps you remember all the stuff. It's kind of like a memory palace kind of thing, actually. If you use your knowledge of real life things in order to help you remember the math terminology. Lava is a higher magma. So I have gotten a little bit more exposed to higher categories over the last year or two, and I wouldn't say that I've done much with higher algebra, but I suppose that okay, this is a little bit of an aside, and then maybe this is just a little bit of an aside, but about the proposition that maybe a lava is a higher magma, right? So for those of you who like categories, in some category C, we have some object A, which was like the set 1 through n in the previous thing, and a magma was basically such an object equipped with a morphism that's like the multiplication from a squared to a, assuming that there is such a thing. Products don't exist in general. Yeah, unfortunately, I don't know how much category theory you should know for algebraic geometry either, because I'm not much of an algebraic geometer. But I do have some general advice for this, which is that category theory is fun, and there's no harm in learning a decent amount of elementary category theory, but it's also a large area, and you can definitely just sort of go off on some sort of random thing or topic in category theory and never really come back. So if your goal is to do algebraic geometry, then I would say that you should definitely focus on what people who like identify themselves as algebraic geometers are actually using. And I would also say that you should, if that's really your goal is algebraic geometry, you should really let the application to algebraic geometry drive your category theory learning. This has the benefit of actually making sure that you learn things that you're going to use, so you both won't forget them after you learn them, and also they'll be useful to you. And it also keeps you from perhaps, depending on your perspective, wasting time getting into things that you never end up actually finding useful. So I think that's just good advice for getting into an area in general, and you say, oh, how much, it could be anything. How much category theory do I need? How much complex analysis do I need? Whatever the thing may be. And, it's often good to try to learn as you're doing the thing that's your real goal, and it will keep you a lot more grounded. It also makes it really intimidating when you say, I want to learn this thing, but you feel like you need to read this whole textbook and this other thing, and you feel like you can never get started. You really should just dive into it. So like if you wanted to, if you could, I actually don't have a specific recommendation for this off the top of my head, but if you can find, if you can, I wouldn't recommend just like going to the NLab or something because it's going to be too much, but if you can find a textbook that's at a good level for you that discusses like maybe, viewing varieties as categories and talks about morphisms of varieties and stuff, then that would be maybe a good way to, get some exposure. But of course, again, just reading elementary category theory can't hurt if you're at the stage where you're starting to learn algebraic geometry. Learning elementary category theory can be a perfectly good complement to just learning the upper undergrad or early graduate math in general. So you really can't go wrong. Okay, so now I'm off on a tangent to a tangent. So if you have a category, you have some object, a magma is whatever a binary operation would be in that category, which for sets in the traditional examples is like this type of thing. It takes pairs of things and it gives you back another thing. And so, the comment was, oh, maybe a lava is a higher magma, this is for traditional categories, which just have objects, which you can think of as dots, and morphisms that are like arrows that go between them. And so, then there's a composition. But instead of having C be a category, if instead C was something called a two-category, then in addition to these one-dimensional arrows, there would also be two-dimensional arrows that go between, go from, maybe that's a bad first picture to do, but in addition to having composites like this, there also might be another arrow that goes along here, and a higher dimensional arrow from this one to this one, and that's a really bad explanation of what a two-category is. But, there's things like this, and then you could ask, well, if I instead had an object in a two-dimensional or higher dimensional category, and, I can still have some kind of map like this, and I guess a priori that doesn't really force anything on you, but then you could maybe say, well, I want maybe something like this with some kind of additional structure that I think of as being the, some natural higher dimensional constraint to put on this, and you could ask that. In this case, I'm not really sure what to say exactly because again, I haven't done a lot of I think what would properly be called higher algebra. Although what I gather is that people put axioms on the higher dimensional morphisms that are somehow natural or appropriate for the for the algebraic structure that they're trying to generalize. But of course, the classical categories are degenerate cases of higher dimensional categories, and so you can always ask for the classical thing in higher dimensional categories without any additional constraints. And since magmas are such a general thing already, off the top of my head, I'm not really sure what else to ask for in this case. But I mean, it's it's a reasonable idea. So if anyone has a good idea or has a better definition of a higher dimensional magma than in the categorical sense than what I just gave, be sure to let me know. I'd be curious to hear. But I think for now I'm gonna leave it at that. Yeah, no, okay, now I'm so tempted, but I'm not gonna mess around with that anymore right now. I wanted to do combinatorics today. Remember back here, a magma, without any sort of fancy generalization, a magma is basically one of these multiplication tables. So there's n squared spots in the table, and there's n choices for each spot, so we have n to the n squared power number of magmas of order n. Okay, so, I mean, there's a little bookkeeping, but that's what I would consider to be an easy thing to count, right? So we just have to count the number of choices and the number of spots, but each of those is pretty doable. And they don't interact with each other in any way, right? So just like in probability, when things are independent of each other, that makes our lives very easy, right? So that's one thing, but we can also ask for a different quantity. So instead, here, maybe I'll go to a new page. So instead, we could ask for something else, which is, well, if you think about it, let's see. Okay, maybe I'll, okay, now I'm trying to think of what example. Yeah, okay, I'll do this. All right, so, okay, so maybe we have this example. This is some magma with two elements, and here is a perhaps different magma with two elements. Okay, and so these are counted different in that count. So to be very specific, the number of magmas in our original setup there with two elements. So the number of magmas of order 2, in other words, means the same thing. Well, that's equal to 2 to the 2 squared from our formula, and so that's 2 to the 4th power, or 16. And these are two different examples of those. So these are not equal to each other. They're not the same table. However, notice that the left-hand one, basically, if you multiply 1 with something, you'll get whatever that thing is back. So this one has that, like, 1 times anything is just that thing. And it also has the fact that if you do 2 times anything, you'll get 2. And then if we look over here, well, if I multiply 1 by anything, I'll just get 1. And if I multiply 2 by anything, then I'll just get back whatever that thing was that I started with. And so if you notice, it's kind of like 1 and 2 have just changed roles. In other words, 1 was an identity element on the left, and now 2 is an identity element over here. And by on the left, I just mean 1 was an identity element for this whole thing, and 2 is an identity element for the second one over here. On the other hand, 2 was an absorbing element, kind of like 0 for the first example, but now 1 is acting like that in the second example. And so, so one way to look at this is to say that, well, even though these aren't literally the same table, these two things are, so maybe I'll just redraw the whole thing really quick. These two things are what we call isomorphic, means like, well, I guess one shape or same shape. And so it's not that they're literally the same, but sort of morally, fundamentally, they have the same kind of algebraic thing going on. And so one way to look at this is like if you take this table and you just swap 1 and 2, then if you just do that everywhere, then you get this. But then notice that the ordering on the table shouldn't really. If I just change where I'm writing down the 1 column and the 2 column, then you'll see I have exactly this. So they're the same up to relabeling. Yeah. So I mean, if I'm only allowed to use the symbols 1 and 2, like I could also use new symbols, and like I could call them A and B instead. But if I'm only allowed to use the symbols 1 and 2, which was kind of my whole setup here originally, then these are the only ones that are isomorphic to these two. Like these two are isomorphic to each other. No other one of the 16 magmas with 2 elements on the set 1 and 2 can be isomorphic to these things. And the way to see that is that I mean, I haven't really given you the proper definition, but it's up to relabeling. And so, yeah, so it's up to relabeling, and there's only one way to relabel 2 things, which is to switch them. So every one of these 16 magmas with 2 elements is either isomorphic to itself when you do the swapping, that's possible, or it has a partner that is like the corresponding table that you get by swapping the symbols 1 and 2. So there are fewer than, the point is there are fewer than 16 magmas of order 2 up to isomorphism, where we take this kind of equivalence into account, where we say that these two are not equal but isomorphic. If we want to count the number of magmas up to isomorphism, this is significantly harder. Now this particular one has been done, and it's not like super advanced, but it does take some work. And now, well, of course, for 2 elements you can do it by brute force. Just check all 16 of them and see which ones have a partner that it's isomorphic to, and which ones are just isomorphic to themselves in a non-trivial way. But there is a formula known for the number of magmas with n elements up to isomorphism, and it's definitely a less trivial formula. Like it's not like I've actually shared the paper before. Oh yeah, of course you can check it with a program, but I want you to notice that it becomes very expensive at some point, right? Because well, as we said, there are n to the n squared magmas not up to isomorphism, is in just the number of different tables. And then there are n factorial ways to relabel and symbols. And so what you would have to do in order to check this manually is something like write down all n to the n squared tables. So just for example, like say n was equal to 10, then you'd have 10 to the 10 squared, so 10 to the 100, so 1 with 100 zeros after it, number of tables to check. And then for each one, you would have to, try relabeling each one, 10 factorial, which is, 10 times 9 times 8 times 7 times 6 times 5 times 4, whatever, you'd have to try relabeling each one that many times. Yeah, so here's the thing. If you want to think about doing it this way, you know, like you can write a program to do this, but I mean, okay, first of all, this, oh, I think I jumped to a different page here. Okay, so first of all, this should scare you if you're writing a computer program. That's the first thing. That 10 to the 100 power should strike fear into you, right? Because it's not going to be fun, you know. Like this, like generally anything that's going to appear in your algorithm that you actually have to go through the whole thing that has an exponent that's larger than the number 2 is going to be really bad. N squared is really, really bad. So that should strike some fear into you. Now you might say, hey, I know some stuff about, coding. I know that I don't need to actually generate everything in memory right away, right? So maybe there's some more clever way that I can just do it one step at a time, and I will end up storing a lot of stuff, but, you know, maybe not everything, right? Well, you know, even if you try to sort of do it iteratively, it's like, okay, I'll make my first table, whatever it is, right? And then I'll look at all of the different possible relabelings. You know, I'll relabel, and I'll relabel, and I'll make some other tables. You know, and then I'll know that I'm done with all the relabelings of these tables. Because then if I were to relabel, you know, then I check, you know, if I was to relabel one of these, well, I should be able to get it by relabeling this, and so, you know, I'll have gotten a whole cluster of them here, right? And then I say, okay, this is one group that are all isomorphic to each other, and then I'll choose a different one. But I mean, at the end of the day, you can probably see that this is going to be agonizing, and I have to store the fact that I already did all of these somehow and check it off my list, and that's going to be really expensive. So it's not reasonable to do this. You can't. Unfortunately, or maybe fortunately, because it makes life more interesting, you can't approach general algebra in this way computationally. There are great ways to use the computer, but listing off every single thing and figuring out the isomorphism classes directly is not fruitful. It's just too big. Yeah, but yeah, I mean, for small cases though, like for some small values, it's doable. But even 3, notice that even 3 is already looking a little bit scarier, right? Because for n equals 3, we have 3 to the 3 squared, so that's already 3 to the 9th power, which is not nothing. Oh yeah, the donut emoji. Yeah, my partner made this awesome 3-hole torus donut sticker that you can use on here. So make sure to avail yourself of that if you haven't already. Yeah, so, alright, okay, so this is all to say that it's way easier to count things without relabeling, or not up to isomorphism, than it is to count them up to isomorphism. That's the general state of things. So it took us, just a couple seconds, even with some side discussions, to get n to the n squared. But I'm not even going to write down the formula for the magmas up to isomorphism, because it's a lot more involved. So let's just not even go there right now. Okay, so that was about magmas in general. But of course, there are some magmas are perhaps more special than other magmas, and so as I often like to talk about, a Latin square, so a Latin square is and so I guess I'll say a Latin square of order n. It's an n by n array where the symbols that are 1 through n appear exactly once in each row, and each column. And so, for instance, okay, well, maybe let me just do it this way. This is a Latin square. This is an order. I guess I should use 3 instead of 0, since I said I would do 1 through n. Okay, this is a Latin square of order 3, according to the definition I just gave. So the question is how is computing the number of objects versus the number of objects up to isomorphism for more objects with more structure. So the answer is that in general both are hard, but yeah, I mean in general both are hard, but up to isomorphism is usually harder. I think that's kind of the general rule. So for instance, the number of magmas is something that it was easier to do it directly. It was harder up to isomorphism. Now, actually, this formula I want to look at, this is going to be for the number of Latin squares, not up to isomorphism. Just the number of sort of like the naive number of objects without taking relabeling into account. And so it's not a long thing, but there's some amount of effort to come up with a formula, and there are a number of different formulas that are known, but it's not it's not as trivial. And then you can expect that the number of finding. I don't know if a formula is known for the number of isomorphism classes of Latin squares of order n, up to the algebraic notion of isomorphism, like for magmas. I feel like that's a thing I should know, whether or not people know that. But if it's known, it's almost certainly going to be harder to figure it out. It's not. I think it's basically never easier to figure out how many things there are up to isomorphism. I'll say that. It's just because one way to think of it is that it's just kind of adding another constraint, right? Like it's adding another constraint to your counting. Adding constraints, unless your constraints somehow trivialize the entire problem and make everything equivalent, which usually isn't happening for interesting classes of objects, adding more constraints is going to make you have to do more work. It's going to be harder. And so for certain classes of things, it's not even known. Like certainly the number of groups, which you can also say are like associative Latin squares with identity, or associative quasi-groups with identity. So the number of those things up to isomorphism, I think, is not known. I think there's no formula that's known. A lot of these questions, even for objects you would encounter in an introductory abstract algebra course, the answer is that we don't actually know. We might have some bounds that are maybe not totally trivial, but we often don't really know, perfectly. And so, yeah. So that's kind of the situation. Like for groups, there are many things that are known, but I don't think that there's actually a formula that's known for how many groups of a given order that there are. It's just a little bit too sensitive to that. So generally adding in more structure makes it harder to count the things. Until you add in so much structure that it becomes trivial. Okay, so that's a Latin square. And then if I had something like this, well, this is not a Latin square because of these two. So this is not a Latin square. Okay. All right. Yeah, so actually I'm gonna, okay, so I want, the formula that I wanted to talk about is the formula for how many Latin squares there are, not up to reordering, so I'm not gonna worry about reordering, because as I said, it basically always makes it harder. But if you want a definition of isomorphic Latin squares, you have to be a little bit careful, because especially the people who are sort of more combinatorial might prefer other notions of equivalence, but what I would say is, like, from my perspective as someone who likes universal algebra and quasi-groups, so the notion of isomorphism that I would use would be the following, is that I would say a quasi-group is, and I'll say I guess I'll say of order n again, is a magma of order n whose multiplication table is a Latin square of order n. And so, like, for instance, you know, before I gave this example, so this would be the corresponding Latin square, and then one, two, three. Let's see, 2, 3, 1, 3, 1, 2. Okay, this would be the corresponding. This would be the corresponding quasi-group, and it's okay if you say quasi-group. That's also fine. Or if you're feeling playful, you can call them crazy groups, because they're, I guess, a more wild version of wild version of groups from intro algebra course. Actually, I'm actually not. I mean, you know, Euler did so many things. I'm actually not familiar with specifically what Euler might have done with them, but Euler did basically everything. So he probably messed around with these too. I would not be at all surprised. But yeah, Latin squares are fun. And so quasi-groups are the algebraic perspective. It's kind of just a matter of terminology, but usually when people say quasi-group, they mean, I want to think about this as like a magma, like a binary operation. And so you just take the table and you just kind of stick on your labels for your rows and your columns, and now you think of it, instead of having a 2 in this position, you think of it as saying 2 times 1 is 2. And that's it. So, okay. Yeah, so that's totally fine. And so, well, now that we have this, we can talk about, so I mentioned before what it was like for two magmas to be isomorphic, right? You can swap the labels and get another table, and that means you found something that's isomorphic to your original one. So if I do the same thing over here, I can find something that's isomorphic to this quasi-group, or this Latin square. And so, well, I'll say that, I'll say just swap 1 and 2 and just leave 3 alone. I don't have to swap 3 around if I don't want to. I can just leave it alone. And so if I do that, then, well, I'll do 2, 1, 3, 2, 1, 3, then 2, 1, and leave 3 alone. 1, leave 3 alone, 2, 3, 2, 1. And then for psychological reasons, if I want to, after swapping them, I can put them back in the order that I want, just to make it, you know, more appealing to me. So 1, 2, 3, 1, 2, 3. And so then, let's see, I have 1 and 1 is 3, 1 and 2 is 1, 1 and 3 is 2. Let's see, 2 and 1 is 1, 2 and 2 is 2, let's see, 2 and 3 is 3, and I can finish out the rest of it similarly. Okay, and so so the corresponding Latin square, if I now go back and think about what the corresponding Latin square is, I don't need the bars, it would be 3, 1, 2, 1, 2, 3, 2, 3, 1. And so I would say that yeah, exactly. That's an excellent point. So when you give a Latin square as a matrix or as an array of symbols, if we're going to talk about this correspondence with quasi-groups, we should always implicitly assume that the rows and columns are being indexed by the symbols in the same order. Otherwise, it doesn't really, the correspondence isn't really very good. So for instance, I wouldn't go back and say, okay, well now I'm going to take this to be an isomorphic Latin square to that original one in the quasi-group sense, because I wouldn't be keeping the same ordering on the labels for the rows and the columns. That's why I'm putting the ordering back the way that it's like supposed to be here. So yeah, that was a great point. That's exactly what's going on. Again, if you're more combinatorial, you might not prefer to think about isomorphism of Latin squares in this sense. There might be some other sense in which you prefer. But if you're an algebraic person, then you probably would say, well, the magma notion of isomorphism is very natural. It's the same kind of isomorphism that we use for other algebraic objects like groups or rings or other things. So I would say though that these two Latin squares here are, you know, that this one and this one are isomorphic as, you know, quasi-groups, or in the algebra sense, those two things are isomorphic. So that's what I mean by one Latin square being isomorphic to another one. But again, I'm not gonna take that into account when I'm looking at this formula, which I haven't actually really looked at yet, but that's the idea. I guess, does anyone have anything else about the what a Latin square is, or quasi-group, or when they're equivalent to each other, or whatever? Although again, I'm not going to be counting them up to that notion of isomorphism because it's harder. I'm just going to count how many there are, like in general, without the relabeling taken into account. All right. Well, yeah. So let me actually take a look at this formula for the number of Latin squares. Okay. So let's see. So I have this paper here, actually the formula was already given up here. Okay, so this is the formula for the number of Latin squares of order n, and they explain what these things are here. And so I will explain in more detail what they are, and actually give some examples. What the difference is between divisibility and invertibility for a magma. Oh, yeah, sure. So yeah, if you look into it, you might notice there's a couple different notions that sound similar to each other at first, but are not actually the same. It's a pretty nice formula. Okay, so what's the difference? Well, if okay, so say okay, no, it's fine. Okay, I'll use 1, 2, and 3. Okay, so say I have 1, 2, and 3 here, and I'm gonna have 1 act like how 1 multiplies for the regular numbers, natural numbers, whatever. 1 times anything is itself, and then I'll have that 2 times 2 is 3. 2 times 3 is going to be 1. 3 times 2 is 1, and 3 times 3 is 2. Okay, so if I do it this way, then this is actually this is actually a quasi-group, right? It's even stronger than a quasi-group. It's a group. So 1 is an identity element. And so that means that 1 times anything is that thing, and anything times 1 is that same thing, right? So that's where I just put the 1, 2, 3, 1, 2, 3 in the first row in the first column. And so I can just always solve x times y equals z for y, say. So like for instance, if you ask me like, well, when is 3 times y equal to 2, I can always find that because I look in the column for 3 times something, and I know that because of the Latin square or quasi-group property, I know that a 2 has to appear in this row somewhere. I see, oh, 3 times 3 is 2. 3 times 3 is 2. So I'm always able to solve that equation. Or I could always solve it for x too. Right? If I asked you, when is x times 2 equal to 3? Well, then I would just look in the 2 column, and I would say, oh, what times 2 is equal to 3? Oh, it's 2. So this is what it means to be divisible. Like you can always solve this equation for either x or y. So this is what it means to be divisible. Or in other words, like you can divide. So the meaning of having inverses is slightly different. So notice they don't, in general, they don't have to have this much structure. So this example that I'm looking at right now is actually a group. So it's a magma which is associative. It has an identity element like this, and it has a property that's even stronger than being divisible that I'm going to talk about now, which is having inverses. So notice that for each well, I guess I'll just say x, there is some y, so that x times y is equal to 1, and that's also equal to y times x. So we can think of y as being like the multiplicative inverse of x. In other words, y is like x inverse, if you were thinking of it as like, multiplication. Yeah, well, even I don't want to get off on too much of a tangent about this one, but any algebraic structure can be ringified in some sense. Even magmas without too much interesting structure can actually be made into at least non-associative rings. But yeah, you would generally at least want the associativity, I suppose. Although, some of us are okay with non-associative rings. But yeah, so, you know, for every x, there's some y that does this. So for instance, well, okay, it's boring that 1 is this thing for itself, right? 1 times 1 is equal to 1. So that's like saying 1 is equal to 1 inverse. But then also notice that, what do I have? 2 times 3 is equal to 1, and 3 times 2 is equal to 1. So that's like saying 2 is equal to 3 inverse, and 3 is equal to 2 inverse. So this is what it means to have inverses. Yeah, so having inverses in this sense means that you have divisibility and an identity element. So that would be enough. For this is having two-sided inverses. You could also have one-sided inverses where you say, oh, I only want something that multiplies to 1 on one side but not on the other. So you'd like get rid of this part. So like there are various versions of this, but yeah, they're very similar. So the point is basically that there are magmas that have no identity element, but they're still divisible. Those are the ones that are quasi-groups, but without identity. And then there are these ones that have inverses, where they have an identity element. And yeah, that is just the condition for I can always solve for y or x, but where z is specifically the identity element. Yeah. So they're similar notions, but they're not the same, because like for instance, maybe I can find one that already doesn't have an identity element. So like, let's see, 1's not an identity. Let's see, 2. Oh no, 2 is an identity here. All right. Well, anyway, there are examples that don't have identity elements. I guess is the point that I want to make. Maybe I won't go through it, but in general, it's possible to not have an identity element. Yeah. So if you have an identity element, well, oh no, I guess if you have an identity element, then this implies this, right? Because if you have an identity element, then just stick that 1 in for z. But going the other way, even if you had this property, you wouldn't necessarily have to have divisibility, because the property about having inverses is just basically saying I have to be able to multiply 2 by something to get 1, 3 by something to get 1, 1 by something to get 1. But that's not really constraining what these products are. So, for instance, if I were to say do the same thing, but instead I were to have still 1, 2, 3, 2, 3, 1, 1. This has an identity in inverses, but it doesn't matter what I put here. So for instance, if I make this 2 and I make this 3, this thing has an identity. This has an identity 1, and it has inverses. Right, 1 is still its own inverse, 2 and 3 are inverses, 3 and 2 are inverses, but this is not divisible. Oh, sorry, I dropped something important that I should mention. I can always uniquely solve this equation. Sorry, that was the important part of the condition that I dropped. So not only can I, well, okay, I guess I should say that to be careful, but it actually amounts to the same thing, because I was thinking, well, now I don't have a unique solution, but I still have a solution to saying 2 times x equals 2. I have two options. I could take x equals 1 or 2 now, but notice I have no solutions to saying 2 times x equals 3, now I have no solutions. So even according to the definition that I gave before, this is not divisible. Yeah. So does that make sense? That's kind of the relationship between those. So you can have an identity and inverses in that sense, but not be. Yeah. But if x times y is equal to 1, oh yeah, yeah. So what you're getting at is that there's a relationship that this has with associativity. Yes. So for instance, so if I know that x times y is equal to 1 in this structure, well, I certainly can find examples where that happens. And I know x times y is equal to 1, and I want to solve 2 times x equals, or let's do a specific example. So like, why is there no solution to 2 times x equals 3, right? Like, or in other words, you might say, well, why don't I stick in for x if I know that if I want to get rid of the 2, and I want to get a 3, I should do like 2 inverse times 3, right? And if we look here, what is 2 inverse? Well, it's actually 3, because 2 times 3 is 1. So if I do this, I get 2 times 3 times 3, and well, that's actually 2 times 3, which is equal to 1, and that's not 3, right? My goal is to get 3. And so the problem is that this is not associative. So it is true that if I do 2 times 2 inverse and then multiply by 3, then I'll get 1 times 3, which is 3, and that's 3. But yeah, non-associative things can have much more complex behavior than the associative ones. That's non-associative things are pretty can be pretty bizarre. These questions get pretty delicate depending on whether you're asking them in the associative or non-associative setting. It can make a really big difference. Oh, and as to the comment about the K-theory intro for group completion, there's a general theme where you can take any algebraic structure that, so there's a couple different sort of, standard things that you can do. And so there are ways of freely generating algebraic structures or freely generating them with some constraints added. And then there are ways of taking the whatever completion, like group completion, ring completion. You can always add back in additional constraints that weren't present in the original structure and get some kind of fixed version of it. Sometimes this sort of destroys it completely and you just get something very boring, but you can always do it. If you like that kind of general nonsense, universal algebra and category theory may be for you. I also talk about that kind of thing a little bit in my division by zero things that I've talked about on the stream before. If you want to check those out, you can find them on YouTube. Non-commuting algebra is definitely harder as well. So even when you have all the nice associativity and stuff, even if you're studying something like groups, which have a lot of structure, the non-commutative ones are much more finicky than the commutative ones. The commutative ones you'll see by the end of like an intro algebra course, at least in the finite case. I mean, well, it's close to the whole story. In the finite case, at least, you definitely should see, and you'll find that you can basically understand what they all look like, and it's not really too big of a deal. I mean, it's the end of the course, but it's like your first course, and it's doable. For the for the finite groups that are not commutative, the structure of those is in some weaker sense understood. I wouldn't say we totally understand them, but in some weaker sense it's understood. But that was the classification of finite simple groups. That was sort of a big important step, and that took a lot of people many years, and people are currently trying to condense the whole proof that we found all of the examples that we needed to understand that part of the structure of what finite groups are like, and that took like hundreds of people, like a century or so to do, and now people are trying to condense their proof, which was originally, I think it was 100,000 pages overall between all the different works. People are trying to condense it down to a sufficiently detailed summary, which is only about 10,000 pages long, I think is the current project. I'm not sure how much it can really be condensed beyond that, but it's an ongoing thing. Of course, the big challenge there is that people are not immortal, and so a lot of this knowledge exists in living human beings, and so huge chunks of it will be lost if everyone passes away who knows about the thing before it gets written down in enough detail that new people can learn it from the book. And so it's in a sensitive place where we feel quite confident as a community that this is correct, but it's possible for us to forget how to do parts of it, and then it may take a lot of effort to rediscover it, because these aren't exactly like straightforward calculations or something that you can just plug into the computer, even with some pretty clever methods. I mean, it's something that took a great deal of sophisticated, like, human intelligence in order to do, and losing it could be very expensive for us in terms of how much energy we have to put back into it. So it's, that was a bit of a tough one, and I'm not really involved in this, by the way. I'll just say I just know the pitch, and it is important. Like, if we made a mistake or if we lose the techniques in order to prove it, it would be a real loss to the to the enterprise of doing abstract algebra. So non-commutative things can be difficult. That's the takeaway. No, it's a real thing. Is if I have to do a bit of a sales pitch for aside from the fact that there's a great deal of math left to discover and new things to do, part of the importance of being a math professor, as opposed to cloistering oneself away in a research lab or whatever, for some company or something. Part of what's important about being a professor, and I'm actually even doing this thing right now, is keeping the living oral tradition of doing mathematics alive, because it doesn't really do us much good for there to be a book or even a computer program. Oh, thanks. It didn't tell me who donated on Ko-Fi, but thank you, someone, whoever you are. I really appreciate it. But this is part of what's important, is because just because a book says something that ostensibly you'd be able to read and understand, or even because a computer program can do the whole calculation and show you that the calculation works, that's not really the same as you having the living knowledge of how to do this discipline, and that is not the same as you being able to generate something new. And so it's really important that we actually maintain and expand on the knowledge that we have, and don't just let it collect dust in a book or on a computer hard drive somewhere, because that's not it's not really helping us to advance or even maintain the current level of knowledge that we have. It requires effort to remember all the stuff that we've come up with in enough detail. I mean, that's the other thing, if I can pontificate a little bit more, is that in order to do those applications, it's not enough just that someone made whatever device or created whatever algorithm once. Things break sometimes, or things need to be updated to be compatible with some new system. Things need to be fixed and repaired and expanded and so forth. And even once the initial application is done, in the sense that someone has created some material thing using mathematical knowledge, the loss of that knowledge can represent a loss of the ability to control our own technology. You've probably seen lots of sci-fi imaginings of what happens when people don't know how to actually operate the inner workings of their own computers or their own devices anymore, and it's not good, right? Like in the short term, maybe people can survive, but in the long term, it's very bad for us. So if I have to sell what I'm up to, it's important that we maintain these skills. It really is felt through all different aspects of our society. It's a form of literacy, Like, imagine if people said we don't need to be able to read anymore because the computer can read everything to us out loud. It's too much work to know how to read. It would be concerning, at least, right? Yeah. All right. So anyway, enough imagining the collapse of civilization, I guess. So let me actually take a look at this formula. Oh yeah. There's always more application to do. There's always more math to find. It's something that you can't really go wrong with. As far as an area to explore. I mean, I'm not going to say that everything's equally applicable, but you generally get a lot of reward for investment in doing math. That's why there's so much money going into it from all the powers that be. Of course, as I've also mentioned, and I don't want to get too political again, but that also ties into the whole thing of like, well, if you want to do math for the public good, you might not be able to get quite as much money as if you want to do math in order to make weapons or what have you, and there's a lot of interesting sociological stuff happening there, but I won't say any more about it. But you probably know how it is. Okay, so let me copy down this formula so that I can start taking it apart. So this is the formula that I wanted to mess around with. So it's n factorial times the sum over some things that I haven't talked about what they are yet. So -1 to something that they called sigma naught of A. And then times this. Okay. So all right. So this is allegedly the formula for the number of those Latin squares of order n. Not with any relabeling, just the number of Latin squares of order n. Well, in order to know what this is, of course, feel free to ask me about anything, but there's 3 parts that I'm going to explain that are the parts that you're most likely to not know what they are, and that's this, whatever this is supposed to be, whatever this is supposed to be, and whatever this is supposed to be. And so, if you take a look at the paper, or I'll just write something down. I'll just write something down here too. So this set Bn is this is n by n matrices with entries 0 or 1. So the only possible choices of entries are 0 and 1 in those matrices. This sigma naught of A, this is the number of zeros in the matrix A. And the most sophisticated, I guess, of the things that are showing up here. So the most sophisticated things that are showing up here are probably these permanents. So the permanent of a matrix. Okay, so it's like the determinant but without the signs. So so this is the sum over from okay. So they had to use sigma for that other symbol. Okay, I'll use tau. I guess I'll say tau in Sn. And then I'll say the entries are little a whatever. So A1, tau of 1, A2, tau of 2, AN, tau of n. Okay. So, okay, so I'll give some examples, I guess, for the permanent first, since, well, okay, I guess let me ask, is there anyone who hasn't seen the determinant before? Obviously, you don't have to tell everyone that you haven't seen the determinant before if you don't choose to, but I'll just maybe briefly say something about the determinant, or what its relation is to this, or I guess on the other, I mean, so just feel free to say if you want, and I'll try to say something helpful, or I guess, have people seen the determinant before? Does somebody want to say if you have seen it before? I mean, you don't have to, but I'm just, trying to assess exactly where people are at. But okay, so I'll maybe just remind you for a 2x2 matrix, which is like the first kind of example that you might see. The determinant of a matrix whose entries are A, B, C, and D is this thing that you would see early on in linear algebra, where you do A times D minus B times C. And if you might remember, this has to do with whether the matrix is invertible and all sorts of stuff like this. And so that's what the determinant would be. And it's given by a formula that's very similar to this, except there's this other factor here that's like a -1 to the -1 to some power. And again, that would be the determinant, not the permanent. But that factor just isn't here. You can also think of it as it's permanent for permutations, because this is saying for each permutation tau, each reordering of 1, 2, 3 up through n, then that's you get one of these terms. Yeah, okay. So, and yeah, that's the geometric thing that that was just mentioned. Also, so the determinant is measuring how much a linear transformation scales the volume of a unit hypercube. Okay, it's signed volume, right? Because you can have the determinant be negative as well as positive, but okay. So yeah, exactly. So there's many ways of looking at it. There's also a purely algebraic description, by the way, of the determinant, which is, I won't write this down, but it's a unique object from the perspective of just pure algebra as well. The determinant is the unique alternating multilinear form on the given vector space, which takes the identity matrix to 1. That's the last condition you need. So there's actually a purely algebraic way to define the determinant as well, and that also leads to the nice formula that is similar to this one. So yeah, there's lots of good ways of viewing the determinant. But yeah, the geometric perspective is definitely a good one to have in mind. So so I actually haven't thought really much about what the geometric perspective is on the permanent. It might just be that there isn't really as good of a perspective, because well, that's what it is. Yeah, the permanent is defined similarly. So in this case, it would be AD plus BC. So it's just basically the determinant, but all the minus signs that are in the formula, you just make them plus signs. That's literally what it is. So you might say, well, why do I care about that? But if you look at it, if you start looking at some examples, if I do the permanent of, I don't know, 0, 1, 0, 1, well, I'm gonna get 0 times 1 plus 0 times 1, or 1 times 0, whatever, and that's gonna give me 0. But on the other hand, if I do the permanent of 0, 1, 1, 0, well then my A and D are both 0, but my B and C are both 1, and so I get 1. And so what I want you to notice is that this thing is what's called a permutation matrix. So there's exactly 1 in each row and each column. So there's other ways of thinking about these, but probably if you've seen determinants, you're likely to have seen at some point permutation matrices as well. If you proceed from the more like linear algebra motivation, if you're thinking more about solving systems of equations and not geometrically, what the determinant of permutation matrices is something that probably has come up as like an important first thing to compute before computing the determinant in general. And so, well, I'm not computing determinants here, but yeah, anyway, this is a permutation matrix, and notice that its permanent was 1. This is not a permutation matrix. This is just some other matrix. And so if I do another permutation matrix, like 1, 0, 0, 1, then, well, this time I'll get 1 times 1 plus 0 times 0, and that'll give me 1 again. So you might guess that the permanent actually is counting something due to permutations, and you would be correct. Well, okay, maybe that's not so shocking because there's permutations in this formula, so that's maybe not really too wild. But then if we look at something like this, well, what if I have the permanent of 1, 0, or sorry, not 1, 0. What if I do the permanent of 1, 1, 1, 1? Well, in that case, I'm going to get 1 times 1 plus 1 times 1, which is 2. And you could actually think of this thing as being the sum of two different permutation matrices. Oh, not that. And so this is like 2 for 2 permutation matrices that are sitting inside of here. In other words, the permanent's like counting how many permutation matrices are inside of your matrix. Now, it's a little bit weirder to say this if you're taking the permanent of a matrix whose entries aren't all zeros and ones, but whatever. I don't really need to worry about that for this anyway, so I won't. But it's basically counting how many permutations are in your matrix is one way of thinking about it. And by n, I mean can be added together to make your matrix. Yeah. So that's the permanent. Well, you know, you might say why, or like, you know, what is going on with this in this formula. But I actually started off before I started the stream. I always like doodle things that are related to what the stream is going to be about, and I had at the beginning of this stream, if I can get all the way back there, we've gone through so many things now. If I can get back up to here, I actually have written down these things now. So, okay, I used a different labeling here than I ended up using. Oh, okay, I'll just write out another example, I guess. But Okay, so basically the idea is that each quasi-group, each Latin square, you can think of as telling us how to add up a certain collection of permutation matrices to get the matrix whose entries are all ones. And so because of that, you would imagine that there is a relationship between these 0, 1 matrices and the number of these Latin squares, at least as possible. And so that's actually what is used in order to produce the formula that I'm talking about. And actually, maybe I'll do some small examples for 2x2s to show you that this formula actually works. So, well, yeah, I'll do it here. All right. So, like for instance, if I have 1, 2, 1, 2, and then 1, 2. 2, 1. Well, that's a 2x2 Latin square, and I can think of like where do ones go? Where do ones go? Well, I can make an array of where ones are in the multiplication part of the table in here, and the ones go in the places that are according to this matrix. And then I can also say similarly, where do 2's go? Well, they go in the other spots. And so then the important thing to note is if I was going to have a Latin square, then each row would have to have a 1 and would have to have a 2. And similarly for each column. And so what is that saying? Well, for each row in the Latin square, there should be a 1 in exactly one of these. So like I look at the first row, right? There should be a 1 in exactly one spot in the first row for each of these matrices. And then similarly for the second row. I know there should be a 1 in exactly one spot in each of these matrices because there has to be a 1 somewhere in the second row and there has to be a 2 somewhere in the second row. And then I can do the same thing for columns. But notice also that it can't be that the 1 in the first row, it can't be in the same place as the 1 in the second row because each entry is either a 1 or a 2. And if like this up here, if this was like 0, 1 instead, it wouldn't make sense because it would say that this entry was a 1, but we also have that it's a 2, and that doesn't make sense. So at the end of the day, that means that having a Latin square of order n is the same thing as saying that we have n, or 2 in this case, permutation matrices, where if we add them up, we'll have a 1 in exactly each possible spot, and so we'll get the matrix that is all ones. So and you can go backwards if you think about it. Like think about what it would mean to have a collection of n matrices like this, or n by n, and have them add up to the matrix whose entries are all ones. You could interpret that as telling you exactly where to put the 1s, 2s, 3s, and so forths into the table to make a Latin square, or a quasi-group. And so if I can count how many ways there are to add up matrices like this, then I will have counted how many Latin squares that there are. Yeah. So that's where this is coming from. I mean, there's still more to it, but that's where this is coming from. Oh, and I'll say also, I haven't gone into it yet, but I don't know if I'll actually end up really getting to it by the end of the stream, but the reason I think it might be possible to generalize this formula to higher dimensional, counting higher dimensional versions of Latin squares, or quasi-groups, is because this is higher dimensional in the sense of like higher dimensional arrays. It's different from the higher dimensional algebra thing we were talking about before, because higher dimensional categories are different from higher dimensional arrays. And so, you know, they're two different notions of higher dimensional. But the reason I think this might generalize well is because I could give a similar description for these higher dimensional Latin cubes, or, you know, for whatever number of dimensions in the cube. It doesn't have to be a 3D cube. It could be like a 10-dimensional cube. I could give a similar correspondence where instead of matrices, I use higher dimensional arrays. So in other words, I have like 2D matrices because I'm looking at a 2D table here. But if I had a 3D table, then I would have 3D matrices, and I would, be adding them up to get the, 3-dimensional matrix that has all ones. Oh, and I guess here I should say too, by like higher dimensional matrix, I don't mean like a matrix with more rows and columns. I mean like one that is like a, this is like a square. These are like squares. I'm thinking of an array that's like a cube. So you might also hear these, oh, that's a horrible looking cube, but you know what I mean. These are also what people call hypermatrices or tensors. Well, anyway, so I think that it's possible to generalize this. But let's see at least that it works. Let's see at least that it works in the original case of just Latin squares first. Okay, so here, maybe if I take this formula, let me see if I can just, can I copy this? I feel like I don't use these functions that let you have convenience things like this so much. Okay, good. Yes. That's very good. What if I hit enter? Will that fix it, or okay. Well, anyway. Yeah, okay, nice. So what's the deal with this? Well, let's at least see that it let's at least see that it works in the case that n is equal to 2. Well, in order to do this calculation, first I have to know what B2 is. Well, remember, these would be 2 by 2 matrices whose entries are all zeros and ones. So we have the all zero matrix. We have this thing. We've got this one. And while I'm doing this, can anyone tell me how many of these things that there are going to be? We actually have already basically seen this calculation. Or does anyone notice what this is actually basically like another version of that we already did earlier? Alright, well, in any case, you've got these ones that have 2 ones in them and blah, blah, blah. I can't actually be bothered to write them all down. Let's see. So, let's see. 256, so 2 to the 8th, right? So the square root to the 4th, 16. Yes. Why did you give me the square root of 256 as opposed to 2 to the 2 squared or 16 or whatever? Just for fun, or? No comment? Alright, well, in any case, I'm not going to write down all 16 of them because it's quite tedious, and so we probably know what we mean. But if I kept going, eventually I'd get to things that looked like, like this, and then eventually I'd just get to the one that's all ones, right? So, oh, just for fun. Okay, just to make me have to do arithmetic in my head. So I can count by powers of 2, but 2 to the 8th didn't come to me instantly. So what I had to think instead was 2 to the 10th is 1024. I remember that because then there's a 10 in the answer too. And then, half of that is 512, and then half of that is 256. So yeah, I can count by powers of 2 up to I think 4096, and then I struggle after that. I have to actually do the arithmetic. It's not like automatic. And then powers of 3, I think even 3 to the 5th, 243 maybe? I I don't have it. I don't think I have it instantly. But it is good to memorize powers, especially powers of 2. But yeah, thanks for that. Thanks for that arithmetic exercise. Yeah. Anyway, 256,000. Is that's the powers of, those are the powers of 2 that you can do? Like if I ask you what is I don't know, like even just like what is 2 to like the 14th power, that's like instantaneous, or like 17th power, like I don't really, yeah. I'm not gonna try to take the logarithm off. Oh, okay. Not like that. I mean, yeah, I can write down powers of 2 in base 2 as well, if that's what you're thinking. Yeah, knowing what it is in base 10 right away is a little bit more work. Okay, so anyway, that's B2. I'm not going to write down all 16 things, but there's 16 things, and so we have to sum up each of those, something for each of those things, right? So now I need to compute sigma naught of A for each of these 16 things. So so let me make this table so that I can do this. And so at first it seems like I'm going to have to put 16 columns or 16 rows in the table, but hopefully we'll realize that there's some way that we can skip a lot of the work and then we won't have to do the work anymore. And I know I'm going to have to compute the permanent of A as well. Well, I'll do that too. So let's get started. So here's some zeros. Well, sigma naught is the number of zeros in the matrix A. So how many zeros are there? There's 4. What's the permanent of A? Well, it's 0 times 0 plus 0 times 0 plus 0 plus 0 times 0 0. Okay, and then let's look at the formula that we have up here. So that means every time that the permanent of A is going to be 0, that this whole thing is going to become 0, and we just don't even have to care about that. So if I ever have one of these matrices and I get that the permanent of A is 0, I'm just not going to have to deal with that. Right? Because I'm going to have to compute 0 choose n, and n is actually 2 in our case. So 0 choose 2, and that's actually just 0. A similar thing is, how many ways are there of doing 1 choose 2? So not 2 choose 1, right? I'm not taking 2 things and choosing 1. I'm taking 1 thing and choosing 2 from it. Yeah. I mean, I think that maybe if you set it up, reasonably, you could discuss some of these things with kids. But I definitely think this formula would be a little bit of a stretch. But each of these things by itself is not actually, that's the way good math goes, right? Each of these things by itself, none of them individually is that onerous. It's just that doing many of them together in a creative way quickly is a different story. And then, well, what's 1 choose 2? If I have one thing and I have to choose 2 from it, I can't do that. So that's also good. So what does that mean? The only time I care about this, the only time I'm going to care about one of these entries is when the permanent is 1 or is 2. Sorry, is 2. In which case I get 2 choose 2, and there's only one way to choose 2 things from 2 things. So okay, So even though this is true, I don't care about this. I just don't care about it when the permanent is not 2. Okay, but then if I go back and look at all these matrices, I didn't write them all down, but how could the permanent possibly be 2? The only way that the permanent could be 2 is if it was this matrix. That's the only way that the permanent's going to be 2, because otherwise there's not going to be 2 permutations inside of your matrix. Okay, so let's take a look at this then. And so yeah, that's so okay, maybe this is misleading because of how small it is, but like this term isn't always just going to give you the all one matrix to look at. Right, so the only thing for 2 is all ones, but this expression is going to get more interesting when n is larger than 2, because there will be matrices that aren't all ones that have more than n permutations sitting inside of them, and maybe I'll show an example of that after this. But this case turns out to be quite small, so it turns out to be quite straightforward. But how many zeros are there in here? Well, there's 0. 0 zeros because there's no zeros in the all one matrix. What's the permanent? It's 1 times 1 plus 1 times 1, which is also just known as 2. Okay, so we thought we had 16 cases to go through and all sorts of stuff to do, but we actually don't care about any of them except for this one. So the only case we care about actually is, well, so for that formula for L2, we actually have 2 factorial, and then we did have a sum, but the sum turned out to the only term that was left in the sum was the term for this choice of the matrix A, and everything else is gone. So then we have -1 to that sigma naught of A, but sigma naught of A is 0, and then we have over here the permanent of A, which turned out to be 2, choose n, which is also 2. Okay, well, 2 choose 2. There's only one way to choose two things from 2 things, and so at the end of the day, this is 1 because anything to the 0 is 1. This is also 1, and this is 2 factorial, which is 2, and lo and behold, this is the correct number of Latin squares of order 2. There's only 2 of them, and we use this formula to check that. So at least that shows that the formula makes sense when n equals 2. Now it's probably more work to show that it still makes sense when n is equal to 3, but maybe I'll at least do a little bit of that just to kind of see what's going on. But yeah, so let's see. So and notice, that what are the 2 Latin squares? Well, if I make the first row 1, 2, that's a possibility. The second row has to be 2, 1, because there's no other choice. And if the first row is 2, 1, the second row would have to be 1, 2, because there's no other choice, and that's all the possibilities. It's just these 2. So there are 2. There are exactly 2. So there are more than 2 Latin squares that are of order 3. And let's maybe think a little bit about what happens when we actually try to do that one instead. Unless there's any other comments or questions about this one. But at least the formula makes sense when n is equal to 2. Okay. So what's going on when n is equal to 3? Let's see. So when n is equal to 3, remember the calculation is basically I have to go through all these matrices A. I have to compute how many zeros are in them. And then I have to also compute I have to also compute the permanent of the matrix. But remember, in the formula, I'm going to have the permanent of the matrix choose n, but if n is 3 here, that means I have the permanent of A choose 3. So this is only going to make sense. This is only going to make sense if the permanent of A. I really want to only look at when the permanent of A is greater than or equal to 3, because otherwise it's not. I'm just going to get 0 for that term because I'm trying to choose too many things. Right, so I really only need to look at these guys for when they have a permanent that's bigger than 3. So like I know off the bat that I don't need to be looking at things like when A is the all 0 matrix, because that's not that's just going to give me 0 for the permanent, and that's not something that I'm interested in, because that term just is going to be 0. So let's think about this. When could the permanent be greater than or equal to 3? Well, perhaps the most natural case to look at is when I just put the all 1 matrix in here like we had before. Now, of course, like before, sigma naught of A is just still 0 because there's no let's see, anything with 2 or 3 1s is discarded. Yeah. So of course, even if you have 3 1s arranged as a permutation matrix, that's a great point. Even if they happen to line up to make a permutation matrix, it's still only one permutation, so you're not going to have it. And of course, if you have fewer ones, like a single 1, 2 1s, whatever, you're not going to have even one permutation, and so that's permanent's definitely too small. So for this one, notice though that even though you could write this as a sum of 3 permutation matrices, like say 1 0 0 0 1 0 0 0 1 plus maybe 0 1 0 0 0 1 1 0 0, and finally the other one, which would be 0 0 1 1 0 0 and 0 1 0. So even though you can do that, the permanent is not 3. This doesn't make the permanent 3, because what the definition of the permanent is actually saying is count the total number of permutation matrices that appear in some way of adding up adding up these matrices to get this. Or more explicitly, the permanent of a 3 by 3 matrix basically says, look at the entries that would be the 1s in any possible permutation matrix and see if they're all 1s in this thing. If they are, then that counts as a permutation that's inside of it. I can do that in more detail, but maybe I won't belabor it, and you can ask if you have more questions, but so at least these are 3 permutations that are sitting inside of this thing, but there are more. So for instance, we also have that you can see this as having let's say, for instance, what have we not done yet? Oh, well, 0 0 1 0 1 0 1 0 0 plus other stuff, right? That's inside of their stuff. So that's another one. Or similarly, well, actually, if you now think of it this way, any permutation matrix is going to be like inside of this one, in the sense that this has the 1s that belong to any permutation matrix, any 3 by 3 permutation matrix. And so, well, there aren't 3, but rather 3 factorial such things, and so there are 6 So it's actually 6. Okay. So you could keep going, but it's just, it's 6. Let's see. So well, now maybe let me go on to do another example. So this was kind of the it's kind of the first thing. Maybe I'll erase this now unless there's any questions about it. Just the scratch work here. Oh, or I could do this in a more intelligent way, I suppose, and just do this. Alright. There we go. Nice. Okay, so now let's try doing something that's not the all-one matrix. Well, what if I do like 0, 1, 1, 1, 1, 1, 1, 1? Well, in this case, sigma naught is 1, and again we have to compute the permanent. So instead of saying let's try to find all of the permutation matrices that like sit inside here in the way I described before, what we could say instead is if we're trying to figure out which permutations belong to this, we could say which permutation matrices are have a 0 here and then other stuff elsewhere, or like that. So that's basically what we're asking. Well, okay, we could say which permutation matrices would fit that pattern, but that's basically the same thing as trying to figure out how many permutation matrices are not like this. So which ones would not contribute? Well, in order for us to figure that out, here maybe I'll go to a next page. So I want something that's not of the form 0 and then other stuff, blah 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 blah. Okay, so in other words, we want a permutation matrix that looks like a 1 and then other stuff, blah blah blah. But well, the only way we can have that is if we have 1 in all zeros and then some other stuff here. And so, well, how could we have this? So we could have this if either we had 1 all zeros and then this one, or the other possibility is that we have this one, and that's it. So, okay, well, that means that there are two things that are not of this form. So there are 2 permutation matrices that are not of this form, and so that means that out of all permutation matrices, 2 of them will not work. And so then that means that there are 4. So there are 4 total permutation matrices that sit inside of this somehow. And so yeah. So you may verify at your leisure that's all of them. I'll leave that for you to do if you would like to actually go through and check that the other permutation matrices sit inside of this, but hopefully you're convinced by this argument, and this is kind of the easier way to see it. So, well, we can keep doing that for all of these, for all of these different terms. But since I'm already 2 hours into this, I'm thinking that I might want to go on to the reasoning behind why the formula works, because I think that actually computing this for each of the other matrices like this would be a little bit time consuming, and I'm not sure that I really want to just sit here and code it and have you watch me code it, which is maybe I think for this one it wouldn't be too rewarding. Okay, but you know, we can do this, and it's natural to ask at this point, okay, like maybe you bought the example for n equals 2, maybe you'll accept or go along with the fact that this can work for n being, 3 or whatever, but, it's natural to ask, but why is it this formula, right? Like, what is going on here? And so I want to actually maybe now take a little bit more of a look at the paper with you, if you would like. Okay, so here it is. So what's going on in this paper? Oh, they actually gave a definition of a permanent there. Well, anyway, so what's going on in this paper? So here when they say, a Latin square is equivalent to an ordered set of distinct permutation matrices that add up to this Jn. This Jn is the all-one matrix that I talked about before. So in other words, that part of the paper is what I did here when I said, oh, look at where the ones go, look at where the twos go. They add up to the all-one matrix. So in that paper, that's where they said, like, okay, P1, they would say, like, okay, P1 plus P2 is equal to J2. So that's that part of the paper. So now what they're doing here is they're saying, okay, so we need to figure out how many ways are there of choosing these permutation matrices, Pi, so that they add up to the all-one matrix. Well, they had also defined these sets Sij, and so, well, I'll give you an example of what one of these Sijs is. So maybe I'll come over here. So, well, okay, it's one of these lists of permutation matrices where, I used Sn to mean the symmetric group, the permutations on n letters, but, okay, I guess, maybe this is a pedantic difference, but here, Sn is the set of n by n permutation matrices, and then S itself they're using to mean all lists of n different permutation matrices from Sn. So just be warned, if you're trying to follow the notation, S is different from Sn and it's different from Sij. I think they overused S here, but So this set Sij, it's all the lists of these matrices with the property that that if you choose a specific coordinate, that coordinate is 0 in all of those permutation matrices. So that's what that is. So, all right. Well, if we look at this, let me see if I can give you an example. Okay, so let's say that n is equal to 2. Let's say n is equal to 3. So let's consider the following list of matrices. Let's do maybe this one. We'll do this one, and then let's do. I guess maybe this one. That's a different matrix. And finally, I'll do this one. Okay, so that's 3 different permutation matrices. So this is one of the elements of the set that they called S in that paper. And like, notice they're all different from each other, right? No two of these matrices are the same matrix. However, this thing belongs to the set S 1, 1, because if I look in the first coordinate of these, they're all 0. So this is a member of the set S11. Well, why would I care about that if I care about Latin squares? Well, actually, is anyone who's following along at home, can you see why I would care about this situation if I wanted to talk about Latin squares? What's Oh, good. Yeah. So it's also a member of S23. So second row. Wait, 2 3. Oh, 3 2. I had just transposed it. Oh. Okay. S3 2. Third row, second entry. Yep. So third row, second column. Yeah. So I mean, it shows up in looking at the permanent. And so, I mean, so that's a part of it, but I guess more specifically, right, what's going on here is that if these three matrices are supposed to correspond to a Latin square, right, like if this is where the 1's locations are, 2's locations, and 3's locations, well, what would the Latin square be that we got? Well, that would mean the 1's go, here, maybe I'll do boxes, right? So if we do the Sudoku box kind of thing, well, where would the 1's go? They would go here, here, and here. And then let's see, where would the 2's go? Okay, now we're having something bad for a slightly different reason. So the 1 has to go in this box, but the 2 also has to go in this box, and they don't want to share the box, so it's not good. But let's just continue, and we'll ignore that for now. So there's a 2 here, there's a 2 here, and then for the 3's, we hit a 3 here, and a 3 here. Oh no, and then this one down here, the 3 also wants to share with the 2. But then notice that there's nothing up here, and there's also nothing down here. And that's the S1. That's what corresponds to S11 and S32. It's saying that if this tuple of permutation matrices is in that set Sij, then that's saying that spot, it doesn't tell us what entry to put in that spot in the Latin square. And then we don't have a Latin square because nothing is put there. And a very similar issue, which isn't really explicitly tracked by these, but which implicitly is also checked, is that if I have something that belongs to S11, that means that there's going to be a symbol, there's going to be a spot in its row and its column that gets a double symbol, that gets assigned the same symbol by two of these permutation matrices here. And so that's why we're getting this thing and this thing. So these sets Sij are keeping track of which entries would not be filled in when we tried to use these permutation matrices to make a Latin square. And so, so what we actually want is we want a bunch of permutation matrices like this that are all different from each other, and that add up to the all one matrix, and we also, one way we can think about this is, well, okay, they wouldn't add up to the all one matrix if one of these tuples was in Sij for some I and some j. There's no way that this can add up to the all one matrix because it's all zeros in the first entry, or in the entry in the 3-2 position. So there's no way that these can add up to the all one matrix. I guess that's the way I want to say it. So, okay. So clearly any tuple that belongs to the set Sij, for any choice of I and j, that's going to be bad for us making a Latin square. So if I have a bunch of these matrices that add up to the all one matrix, then I want to say that for any specific entry, Ij, like 1 1, 2 3, whatever, the entries can't all be 0, because if they were all 0, I would have something that doesn't work for making a Latin square. And so saying that they're not all 0, at least one of them is 1, means that tuple has to be not in any of these Sij. So sorry, there's a couple different negations going on here, but the point is that if I look at these sets Sij, these are like the bad tuples. If I look at the ones that are not in Sij, then those would be good for that coordinate. And if I have something that's good for every coordinate, the every makes the intersection, then I know that I have a good list of permutation matrices. So I don't know how much I want to really go on about like restating it, but you can, if you want, if you're not already convinced, you can sit down and convince yourself harder that this condition is actually equivalent to saying that I have a list of permutation matrices that is not in any of the Sij. And so that means that if I wanted to count how many Latin squares there were, that I could look at what the size is of the intersection of all of these Sij complement. So if I could compute that, then I would be doing good. You might wonder, like, how does it help me to know this? How does having this expression for it make it better? But it turns out that it does. So there's still a little bit more to it, but the thing I want to say first, I guess, before going on, is that this is now using inclusion exclusion. Okay, does it work similarly when you add them as matrices? If you get 0 mod 2, then it wouldn't work as well for similar Sij. So I'm not really sure. So, okay, if you have two of these things and you add them mod 2, the only way that you're going to get all zeros would be the only way that you're going to get all zeros would be if it was the same one with itself. But if you just meant 0 in that coordinate, well, that's true. So, like, for instance, if I add 0, 1, 1, well, okay, maybe this. Nah, I want a not boring example. Oh. I want a not boring example, so let me do a bigger one. So if I do, like for each entry. So okay, so you could say instead. You could say an analogous thing, which is like, okay, instead of Sij, I'll define like Tij or something to be like the the tuples where there are, like, I guess at least two matrices with there are at least two matrices with like P, well, okay, I'll just say like P I guess I'll say like PUIJ is equal to PVIJ is equal to 1. So like you could say it like this, like I want to consider these sets of these tuples of matrices where two of the matrices are telling me to put a different symbol in the same spot. And of course that's going to happen, like that's going to happen whenever there's something in that row or column that doesn't get anything at all. And so you could also think of it from this perspective as well if you'd like. I'm not really sure whether there's an advantage or a disadvantage to doing so, but you can see from this picture hopefully that it's very related, right? Like this tuple would be an S11 and S32, but if I define Tij to be like this, then it would also belong to like T12 and it would also belong to T31. For similar reasons. Yeah, I mean it's just kind of a question of perspective, I think. But I'm gonna follow the one that the authors took, I suppose. But I mean, it's a reasonable thing to ask. I want to try to just follow what they did, but yeah. I mean, it doesn't seem obvious to me whether one should prefer one way or the other at the moment. Yeah. But yeah, I mean, I would. Yeah. I would imagine that it would be quite similar. Actually, I mean, I guess, but by what I said, no, yeah, wait, not just quite similar, but by what I just said, okay, I should be careful. There is some very close correspondence between these sets, right? It's not that there's like a correspondence where, like, if I know something is an S11, then I know it's in T sub ij for some specific I and j. But I do know it's got to belong to some Tij, because that whatever entry would have gone in the 1-1 spot has to go somewhere else in that row in that column. So like it's I'm not sure whether like it would be just as easy to go through the whole proof using these Tij instead of the Sij, but it should at least it is a very similar idea. Yeah. So, yeah, I haven't tried it, so I don't know what happened. All right. So, the next step. So there was some kind of correspondence to the intersection of these complements of these Sij, the tuples that don't belong to any of the Sij, right? And so the next step is to use inclusion-exclusion, and okay, hopefully by the end of my time, I will at least have described this next part of the idea in more detail, and that'll take us pretty close to the end of at least seeing how this works. And if there's sufficient interest, or if I feel like it, or whatever, I can also just try to sit down and actually do the generalization a different time. But it's always a balance where I try to remain reasonably accessible. My audience varies from week to week as to how much math background people have, and so I also don't want to just dive into something where people are immediately like, "What are you doing?" and it takes time to explain. So I try to find that balance, but I've been having fun doing this, and I think it's good for me to go over this in detail before trying to generalize. So but so far I haven't seen anything that seems like I couldn't do it for higher dimensional hypermatrices. Is basically the point. So that seems promising. All right, so I'm not going to sit here and write down the corresponding definitions, but maybe you can believe along with me that it's pretty reasonable. Instead of, for instance, like here, instead of Sijs, you'd have Sijks if you were doing the three-dimensional version of it, because coordinates in a three-dimensional array have three things in them. Yeah. So I guess I have enough room here. Okay. Yeah, I mean, it depends on what part of algebra you're in, but generally speaking, a lot of parts of algebra are pretty close to combinatorics, where like, especially once you have linear algebra, you really have most of the tools that you need to go pretty far, and so that's really nice because I mean different it's different. Different strokes for different folks, different areas appeal to different people, but I do like some things that take a little bit more background, like algebraic topology takes a little bit more to get into perhaps, but it's always really nice when you have these areas that are, very down to earth. There's like discrete finite objects. It's, stuff that you don't really need to have a lot of formal background to see the picture and kind of get what's going on, and that's really nice because it can, maybe not perfectly, but it does kind of level the playing field in the sense of like, these areas that have a lot more background required, that means that you have to invest a lot more time and energy before you can start even looking at the questions, and it creates this barrier that people say, I don't have the time, I don't have the resources, or just for like social reasons, like I haven't gotten along with anyone in the area well enough to put in the time to get good at it. And so it's like, and getting good at it just means basically being able to, being able to understand what the questions are. And so like that's, that can be off-putting to people. So yeah, that's why I think combinatorics is so big, because you can just get into it. You don't have to spend years and years before you can understand the definitions of things that you want to use all the time. Yeah, and so it takes all kinds, but definitely it's nice. And that's also why I like general algebra, because it's true you should have some algebra, abstract algebra background to start doing it, but strictly speaking, if you can understand sets and functions, you can understand, you can start learning general algebra. And so that's, I always found that to be really nice. Yeah, so, okay, so I wanted to talk about inclusion, exclusion. And so, so I would like to tell you, remind you, whatever, that, do you remember being given these, like, puzzles, like, in school or something, where it's like, oh, like, there's like, I don't know, there's like 30, there's 30 kids signed up for class A, and there's I don't know, there's 20 kids signed up for class B, and this is class B, and and then there's like, I don't know, they would give you some other information, but like, I guess, okay, before getting into that, I guess the first thing is, right, there's 30 kids in class A, there's 20 kids in class B, with no other information. You can't determine, you can't determine how many kids are in like the whole, in either class, right, in the whole school or whatever, because of course it's possible that there's 30 kids over here and there's 20 kids over here, but there's nobody who's taking both classes because they're at the same time or whatever. But it's also possible that it's split up some other way, and there's 10 kids that are in both classes, and there's 10 over here, and there's 20 over here. And so, you can't count the total number that way, right? And so, so in order to know the size of the union, well, it's not actually enough to know just the size of A and the size of B, but you also have to take away the size of their intersection if you want to know how many people there are, right? Because if I add up the things that are in A and the things that are in B, I've counted everyone who's in the middle twice. I've counted them once for when they're in class A and once for when they're in class B, but I only wanted to count each student once. And so I've overcounted the ones that are in the middle, and I have to take away that number in order to fix it, right? Like here, the total number, it wouldn't be 30 plus 20. It would be, like, in the example that I just gave here, it'd be 30 plus 20 minus the 10 that are in both classes, because that 10 appeared in this 30 and also in this 20, and that's it should only have appeared once. So, that would give me the proper number, which, in this case, as you can see, would be 40, right? So, that's inclusion, exclusion. But now you want to do it for, not just 2 sets or 3 sets, but for n sets, right? So, so how do we do that? Well, here, maybe I'll just go to new page. So what's the next level? And then once we see the next level, we should hopefully feel pretty good about, why it's happening like this in general. Okay, so here's A, here's B, and here's C. Okay, so what happens if I do all the stuff in A plus all the stuff in B plus all the stuff in C? If I do all of that stuff, then okay, this is counted. This like segment of the Venn diagram is counted once. Each of these things is counted once, right? Because they each belong to one of the sets here. But then if I look at, say, this piece over here, this one's counted twice because it's counted once as belonging to A and then once as belonging to C. This thing is also counted twice, and so is this one. Whereas this one is counted 3 times. Okay, so now what if instead of doing this, okay, so instead of doing that, I want to do something similar, but I'll say, okay, well, I saw the previous example, and it looks like I should subtract off the intersections. Here, let me draw a better Venn diagram. I want room to actually draw what I need to draw. So okay, that's better. So okay, I'll try to do not just adding up how much stuff is in A, B, and C, but I'll try to subtract off. I'll subtract off all the pairwise intersections. I'll do A intersect B. I'll subtract off the size of A intersect C, and I'll subtract off the size of B intersect C. Yeah, so I have to take away all these intersections, but now something new happens. So I've still counted everything in A, B, and C, like outside here. I've counted each of these parts once. But if I take away these, well, let's think about this. In the previous thing, each of these little triangular kind of segments was counted twice. So if I take away each of these, then each of these should only be counted once. But now I have a new problem, which is that I had counted everything that was in the intersection of all three times, right? I had counted it 3 times because it appeared once in A, once in B, once in C. But now, look, anything that was in the middle, exact middle, that was in A intersect B intersect C, I had now taken it away 3 times because I took it away once here, and then I took it away once here, and then I took it away once here. So now I've actually counted this 0 times because, I got 3 copies of each thing that was in the middle, and then I threw away 3 copies. So this is still wrong. Well, how can we fix it? Well, we can just stick back in everything that was in the middle. And so now if I redraw my picture for the last time, well, if I want to stick back everything in the middle, I can do, here, that's not a minus sign, I'm just being messy. So we can do the size of A plus the size of B plus the size of C minus A intersect B minus A intersect C minus B intersect C, and then I'll just do plus the size of A and A intersect B intersect C. Okay, so it's basically like each of the sets. If you just have the set by itself, or you have the intersection of an odd number of sets. The set by itself is like the intersection of a single set, just by itself. Then they get plus signs. But if you have the intersection of an even number of sets, then they get minus signs. This is inclusion-exclusion. It's like I include all this, but then I have to exclude this, but then I have to re-include this because I have to fix it. But when I do that, I see that I actually count everything the appropriate number of times. So I'm just going to put ones here to keep with my scheme. And so this is actually correct. And so similarly, we can do this for any number of sets, and we'll just find that it keeps alternating. It keeps alternating like this. And so so that's inclusion exclusion. And so that's why you know, that's also why it's also why we need inclusion exclusion here as well, because we're going to use we're going to use a similar kind of thing. Here, let me just do that. Okay, so so if you look at this, so we want to find so first, the problem was overcounting, but then when you try to do the solution, when you try to do the same thing the next time, then it became undercounting, and so then you have to add in something else again, but then at the next level you have the opposite problem where you've overcounted, and then you need to subtract something, and it keeps balancing out like that. So, okay. So remember, these SIJs were the lists of permutation matrices that did not do the correct thing when that we're missing one of the entries, right? Like, so maybe I'll just go back up here to remind you. Remember, it's like this list of permutation matrices where none of these matrices have a 1 in, say, the 1, 1 spot, and so it doesn't tell us what symbol to put there. So we want all the lists of permutation matrices that do not belong to any of the Sij for any choice of ij. And so, well, that means that we want the intersection of the complements of all of those sets. So the things that are not in the Sij for each of the Sij. And so now they start introducing notation that will be helpful with this. So maybe I'll come back to that in a minute. So let me actually, okay, well, I guess I'll just go actually to the final formula. So what is happening here is that this -1 to some power, these are the plus and minus signs from doing inclusion exclusion. And then these are the sizes of the intersections of the sets in question. So that's like what's happening here. Or I guess we can also look over here. So okay, so if I come back and I say, all right, so they're saying consider some x that's a set of positions in the n by n matrices, and look at the intersection of the Sij for all of those x. So what would that intersection look like? So these would be tuples of permutations that were bad for the coordinates ij for all possible ij in this set x. Okay, so maybe I'll give an example, since that's kind of it's kind of a whole thing. All right, so I will give an example of that. So So let's say that x is let's say that x is 1, 1 and 3, 2. It's a perfectly good set of coordinates. And if we do this, then we're going to say that so Sx would be, in this case, it would be S11 intersect S32. Well, we actually already know something that belongs to the set, which I chose because of this. So this particular list of permutation matrices is in S11 and S32. So it would be in Sx for that choice of x. And so what is this in general? It's tuples, or I guess since we're working with the n equals 3 case, it's triples of permutation matrices like, so we know the 1, 1 coordinate is always 0, and then there's some other stuff, and we also know the 3, 2 coordinate is always 0, and then there's some other stuff. So that's what Sx looks like for this choice of coordinates. And because of the condition that these are that these are supposed to be lists of different permutation matrices, some of these Sx's will not have anything in them. Like that's possible. Like if you just put in all the coordinates, for instance, like S, like S, where the subscript here is just like all possible coordinates. So like all pairs coordinates. Then this is just list of permutation matrices where all of the entries are 0, and this is just there's no such thing. So some of these just don't actually have anything in them, but there are some that are possible. Like we know that Sx for this choice of x exists. Like there's something that's in it. It's not empty. So that's what these things are. And then so then you can say, okay, well, if I want to have a list of permutations that actually defines a Latin square, what relation does that have to this? Well, certainly it would have to not belong to any Sx, right? If it belonged to any one of the X's for any choice of x, then that list of permutations wouldn't work. So the reason why we like this for counting is that well, let me draw a picture. If I can go to a new page. So let me think back to the n equals 2 case for a minute. That means that the possible coordinates are 1, 1, 1, 2, 2, 1, and 2, 2. So maybe we well, how do I say this? So which things are bad? Like which things wouldn't we want to look at? Well, there's things that are in S11 that fail because none of them put an entry in the 1, 1 coordinate, and then there's also things that are like in S12, and maybe there's some overlap, and there's also like S21, and maybe there's also let me see if I can draw this properly. I don't think I did, but well, let's see. Anyway, there's and then there would be S22 also. I'm not gonna feel like I'm not going to end up actually drawing the Venn diagram properly, so I'm not going to try, but, you know, there's also an S22 as well, right? And then, well, we can't just figure out which lists are the bad lists of 0, 1, or of permutation matrices by adding up how big all of these guys are, because of the thing about inclusion exclusion, right? If we just add up how big, we can't just add up how big S11 and S12 and S1, you know, S21 and S22 is to figure out how many of the like bad lists of permutations there are, because we need to use inclusion exclusion. And so that's what, you know, that's what the point of you know, that's what the point of defining, if we're going to ask about the intersections, right? This is like Sx, where x is, you know, 1, 1 and 2, 1, for instance. And so if we know the sizes of all of these, then we'll be able to figure out the sizes of the intersections, and so then we'll be able to use inclusion exclusion. But we don't just need the pairwise intersections. Remember, we need any number of them intersecting, and so that's why it's Sx for any choice of coordinates, because we need all of those numbers to use inclusion exclusion. And so then we come back over here. Okay, and so all right. So then what is this? What is this actually saying here? Well, it's saying by inclusion exclusion, but as I just mentioned, that's actually counting something that is like not the thing that we want. So there is a little bit of reasoning left as to why this is the correct quantity. I'm now a little bit concerned, actually. So let's double check that this is what we want, because yeah, so we want the size of the intersection of all of these complements. Oh yeah, but okay, if something's in at least one of the Sij, then it's not in Sij complement, and therefore it's not in the intersection. Sorry, if something's in one of the Sij, if something is bad means being in one of the Sij, then it's not in the complement, and so then it's not in the intersection, and so then we wouldn't count it. Everything that survives this process, we would. So, okay, so that's making me feel like what this is actually supposed to be counting is, if I wanted to use inclusion, exclusion to count the size of the intersection of, no. Because if I want to count the size of the intersection of all of these guys, okay, this is the last step of reasoning that was missing. So, so why am I intersecting the Sij? And so, so if I'm counting the intersection of the complements, then here, let me draw a picture to show you. So, because I want to make this not mysterious. Okay, so say I again have my sets A and B, and instead of finding the size of A union B, I want to find the size of like A complement intersect B complement. And so that would be like, I want to find the size of all of the stuff that's not in A and also not in B. So I want all the stuff that's in whatever my ambient set is, which was like, I think S in the paper. I want all the stuff that's not in A and also not in B. And so, well, that's asking me for the size of an intersection. I don't want to say this. Yeah, so I feel like there's one complementation that's not been addressed here. So, oh, I guess the complementation is I did like the union. There's like an intersection version of this. And there's a union version of this. So, okay. That's the part that I had skipped. So, okay. So if I want to figure out how much stuff is not in A and how much stuff is not in B, well, I can't. This isn't just the same as saying take everything that's not in A. I can't just say like look at the size of everything that's not in A. I can't just look at A complement and say, okay, I have all the stuff that's not in A, and then I add it to all the stuff that's not in B, right? Because I'll have the same kind of double counting issue, right? So, I can't just take everything that's not in A and add it to what's not in B, because anything that's not in A and also not in B will be counted twice. But then the stuff that's not in A but is in B will be counted once in the A complement part, and the stuff that's in A but not B will be counted once in the B complement part. So again, there's something is wrong, right? Well, how can I deal with this? One thing that I could try doing is I could think, well, I mean, what else can I do, right? I could remove like A union B. I could remove A union B complement because then if I took if I took the union of them and I look at its complement, then I'll have one thing left. But then I still have overcounted. I'll still have overcounted here. So A union B should be 14 for n equals 2 for the bad ones. Or yeah, here, let me actually just, okay, actually instead of like laboriously doing it for this, yeah, it would be better to just let me just do the actual case that we're considering, instead of trying to make it more abstract to separate it out. So if you have the idea for inclusion exclusion from the previous thing, that's perfect. It's just a question of how do we translate that into the situation that we're looking at, right? So what we're being told to do is to use this formula when we're taking these sets Sij and we're looking at, we know that we're going to compute the sizes of all of their various iterated intersections. And so the question is, why is it that inclusion exclusion is telling us that this is the total size, right? That's the question. Um, so so in the so in the n equals 2 case, remember S11 would be like those lists of matrices which do not have any entries, any ones in the 1, 1 coordinate, for instance, right? So we don't want to include. So we don't want to include that quantity. And so now, if we actually look at where that would show up in the formula, that would be a choice of x where there's only a single coordinate in it, right? So the size of x would be 1, and we get -1 times the size of this subtraction. This was the thing that I was like, where is this? Okay, I was missing where this subtraction came from, and that's why I started going, there must be like some kind of complement version of it that we can state, but we don't have to think of a different version of inclusion exclusion. I found what was bothering me, I think. So if we look at this exponent, if we just have a single coordinate like 1, 1 or like 3, 2, then we'll get a -1 here, right? Because the size of our set x will be 1. And so what's happening is that if you remember back when I described inclusion exclusion to you before, the way that I was thinking of it, which is like to prejudice it, the normal way of thinking of it, then we saw that the original sets were they were added together, not subtracted, right? So here's what's going on. I'm so glad I caught this. See, this is the type of thing that, like, if you're deluding yourself and you just want to like fly through everything and say, yes, I understand perfectly, I don't even have to worry about it, then you'll skip details like this, and like, it might not look too pretty sometimes, but making sure that you understand those little details is like that's where your fortunes are made, like that's really what separates people who are trying from people who are not, and it might feel really good in the moment to say, oh yes, it's obvious, clearly I understand that, and just not worry about it, but these things are the things that get you. And so that's why I thought initially I could explain it a different way, and I realize now the better explanation, and I'm happy, and I feel like I've actually made I've done something good. You've gotta be. It's a balance, right? You've got to have confidence to go on and try new things and see what's out there, but you've also got to have enough. You've got to be critical of yourself enough that you can check that you actually are there. And so, so if I was writing this paper, I would have maybe made a comment about the fact that this is what's happening. I know it's not a huge thing, and maybe to these authors, that they're wherever they were, it's just a short note. It wasn't a big deal to them, they just weren't, whatever. But notice what's happening here is that I'm allowed to choose x to be an empty subset of coordinates. So, right, because I can just choose any subset of the positions. The trick is that I'm allowed to choose an empty subset of positions. Which also, for those of you who are empty set, fans who are always like, oh, but how does this work when it's the empty set? This is also a good thing to remark upon. I can choose an empty set of coordinates. I just don't choose any of the coordinates. What is xx in this case? Xx is the intersection of all of the Sij, where ij is in x. X is the empty set, so there are no ij. This is the empty intersection. And if I have the empty intersection, you can think of it like an empty product. And so I should get the identity for intersection. I should get the thing where you intersect with it and you get the same thing back. That is the whole universe. Remember, this is this S. These are all tuples of distinct permutations. And this was the part that was giving me problems, because I was thinking, like, wait, what's, the inclusion exclusion isn't exactly in the form that I just presented to you. That's because they were sneaky and they snuck in this S that was the universe by allowing us to take an empty set of coordinates. And so when you actually look at what this is saying, the way I might have written it at first for the reader to make it a little more clear is that I would have said the total number of Latin squares is the size of the total number of all of the tuples of permutations minus the bad ones and so then what are the bad ones? The bad ones are the ones that would be in the union of all of the Sij, but there's some trickery going on here, right? Because if I wanted to, I could actually write this. If I wanted to, I could actually write this as minus the size of the union over all x that's not the empty set of the Sx. But then I could say, oh, but this is the one for the empty set, and therefore it's very similar to the formula that you would have before, right? So this would be minus the sum over all x not equal to the empty set of -1 to the size of x, I guess -1. So there's a sign that's different, right? Because if I put in a single thing, right? If I put in a single coordinate, I should be getting a positive contribution. So like, in other words, if I chose a single coordinate, I went too far. If I chose a single coordinate, that's like choosing just a single one of these big sets, and there should be plus signs here. So that's why I have to do the number of coordinates -1 or +1, because I have to make it even when x has an odd size. So it would be this times the size of Sx. But then you say, but this is the empty set case, and this minus sign is going to get rid of this -1. So at the end of the day, we actually just have the sum over all x that are not the sorry, that was the whole thing I just went through. Sum over all x, which can be the empty set, of -1 to the size of x times the size of Sx. Okay, and so I wanted to apologize for having gotten tripped up by this. I knew that something wasn't right, but my first attempt was to say, let me state a slightly different version of the inclusion-exclusion, and then I was like, no, this isn't going to be good. This is exactly what they meant. I'm certain of it, and they didn't include that, but that's part of what reading a paper is. And I was going to apologize, but I now realize watching me do that process is probably actually really, really good. Because you might also wonder, okay, well, I don't know if you wonder this, but in case you do, you might wonder, you're so fancy, you're a professor at some nice school, everything, you've got these papers and all this stuff going on, you must just instantaneously read all of this and not ever fumble over anything, not ever try to sit there and unravel something and make sure that you understand all the details. But I do. I actually, it doesn't always look pretty, but I am a human being, and I sit there and I try to make sure that I understand each of the pieces, and that's how you get good, So, yeah, I mean, I hope that was helpful to you, or it was at least entertaining. And so now that we're at this stage, I think I'd just like to make a couple more comments before calling it. Of course, still ask me if you have any last questions or comments that you want to make or anything, and I'll be happy to address them as time allows. Yeah, just get good. Just get good. It's just that easy. So so there was a little bit of finagling because we had to actually sneak the ambient set S with no subscript in. But this is indeed using inclusion exclusion for that formula. Yeah, and thanks for all the thanks for all the triple donuts. So so the whole deal then becomes counting the sizes of these SXs. Yeah, this paper was published a few years before I was born, so I am not certain that anyone will get right back to you. Oh, but I did find, okay, this is a small aside thing. I once found a mistake in okay, so there's a Springer textbook, which is, I'm not going to remember. I think it's it's like something like an algebraic introduction to mathematical logic or something like this. And the book was from the 70s, I think, and it's a Springer. It's graduate text in mathematics, right? So it's the big yellow books. So it's that series, and it was graduate text in mathematics. So this is like the big series that are like these are like the good books, right? Like. And so it was. It's one of the first ones in the list too. It's like one of the lowest numbers, I think. And there are two authors, and it introduces mathematical logic and universal algebra, and like has like the algebraic logic perspective, like from universal algebra. And one of the first exercises in the book is wrong, as in the statement of what it's asking you to prove is false. And it's a fact about universal algebra. Like it's some exercise in universal algebra, but the statement is wrong. Like there's no easy correction. It's not a typo. There's no like slight correction that is going to make it a good exercise. It's just a bad exercise. And so I noticed this at some point, and I emailed I noticed it. I mentioned it to some people. And I was in grad school at the time, I think, and they were like, "You should email the authors." I'm like, "This book was published like decades, many decades ago. Like they don't care. No one cares, right?" Well, I found the author's emails. One of them didn't get back to me. One did, and he said that it was really more the other guy's project. He's not as much of an algebraist, and like he didn't know exactly how it happened, but he agreed that the exercise was bad. We talked about some possible like fixes, but like it was one of these things. I can't get into it in like just 2 minutes, but it was one of these things where it was clear that there was an intent here that like I had mentioned it to like maybe another grad student, and they had been like, "Oh, didn't they mean this?" And I'm like, "Yeah, but that doesn't make sense. Like that's like it's clear that that's what they were thinking, but it doesn't work." And like anyway, I can't get into the details, but the guy was just basically like, it's a bad exercise. We went back and forth a little bit and talked about possible modifications or what they could have meant, and it was nice, and I really appreciated the response, I guess. I don't think they're ever going to publish an erratum about it or anything. I think it's just the bad exercise in that book that you have to know is not correct, and that's just what it is. Yeah, I mean, people will surprise you. I mean, I shouldn't just totally dismiss the idea. In this case, they'll just say, we weren't wrong, we just didn't bother to tell you that, and you figured it out, so, like, that's fine. But yeah, people will email you back, even like 20 or 40 years later sometimes, which is wild. Yeah, it's a good thing to do if you care about maintaining the textbooks and you want people to actually use them. I mean, okay, maybe one more story before wrapping up, but as far as the math here goes, I was just going to say, so the rest of this is counting the size of these SXs, and they do that here, and it's doable, and you get the formula. So if I come back to this another time, now that I've explained it, what I'm going to try to do is go through and define all of these things for the higher dimensional hypermatrices instead, and see if I can compute the same quantities. It looks like the argument should go through in that case basically the same way it does here. The question is if I can count the higher dimensional versions of these sets SX the same way. I think I can define the higher dimensional version of the permanent, but we'll just have to see. But anyway, yeah, I guess the one other comment before I go, also when I was in grad school, I remember taking a real analysis course, and we used, oh no, maybe this was undergrad. I was in undergrad. I was taking graduate real analysis, and I remember that we were using Royd and Fitzpatrick, and there were so many mistakes in Royd and Fitzpatrick, like so many mistakes in the text, the exercises, and all of it. And at some point during the course, people were like, started being like, yeah, so we know why it's so bad now. It's because like Royden died, and then Fitzpatrick finished up the manuscript that he already had, written up a fair amount, but there was still lots of editing to do, and Royden had died, and so he didn't, Fitzpatrick didn't, manage to do it properly. It's hard to take someone else's half-finished book and finish it and make sure that there's no mistakes, and, yeah, so that's what happened, and we used it, and, like, it's not, like, the worst thing ever. Like, it's not terrible. I actually like the setup more than my professor did, actually. Like, they go through defining a series of different integrals instead of just doing it all at once. I think it was actually quite nice. But anyway, like, because it's just psychologically it was easier instead of just saying like, oh, here's the vague integration, like just as like one thing, and all the proofs have all these parts. Like, anyway, I just liked it better. But there were tons of mistakes. Professor never wanted to use the book again. Like, it was totally understandable, but yeah, I mean, it's just things get published with mistakes all the time. Not just omissions that might have been helpful, but like legit mistakes. Yeah. But anyway, oh yeah, and I see that I haven't read this algebraic number theory. I think I take it that's algebraic number theory book. But yeah, it's unfortunately, you want to get people's last work out there. It's part of their legacy and everything. But unfortunately, sometimes that means that we end up having to learn by correcting mistakes in the textbook, and that's life. Okay, well, I'm a little bit over from the time that I had allocated, so I really appreciate everybody stopping by and saying hi and everything. Well, oh, there's the chat again. As I am getting back to it. So for me, classes will start again next week, but they line up, my schedule lines up good to keep doing this time, so I hope to keep live streaming and keep having more cool interactions and doing more math. So yeah, thanks everyone so much, and have a great rest of your day or evening or whatever it is, wherever you are. Alright. Yeah, thanks. See ya.